All right, good morning, everyone. So today we're going to talk about something a little different. Yesterday we mentioned that we've been working, both of us, on several UI toolkits in our career, so we decided, hey, why not write a new one? So the idea here is to demystify UI toolkits. You know, they're those like big libraries full of widgets and APIs, and they look very scary and complicated. And so we're just going to present a new UI toolkit, like I said, that we wrote, just to show you that they're actually really, really simple and that you shouldn't be scared of them. And hopefully that will encourage you to look at the implementation of the next UI toolkit that you use, be it Compose or the view system or whatever else. So we'll get started. After this talk, or during the talk, if you want, you can go check it out on GitHub. So it's /romain/experiment-apex. You can download the source code. Don't expect any comments. It's a very small toy, but you should be able to study it to learn a few things.
So let's talk about what UI toolkits are. They're really simple in concept. They are a way of presenting visual information to the user, and they're a way of getting inputs from the user to interact with that visual information. Specifically, we have the opportunity to organize the layout so you can actually structure the visual information on the screen. You need the ability to actually render that onto whatever the native platform is there. And you need the ability to find out when the user is interacting with these elements on the screen so that then the button can be clicked, the image can be slid away, whatever it is. So let's take a look at a tiny example. This is the sample from the Apex project if you want to check it out. So here we have, typical sort of hello world kind of thing. We got an image and we have a couple of buttons. Visually in the layout it looks something like this. So we have a column and then we have an image as the first item and then we have a row layout below that in which we have the two buttons.
Yeah, and what's important here is that and it's common to pretty much all UI toolkits, the way you represent the UI in memory and logically is as a tree. It seems pretty obvious. You have, if you're used to it, you have a view, you add view children to it, and then the UI toolkit will traverse that. But that's pretty important because there are multiple ways that you can actually build a UI toolkit to recreate that tree. So here we have the view system, our oldest API. That's what it looks like when you use it from code. And this is an imperative way of declaring UIs. You have to manually and explicitly do everything, right? So in this case, we have to create a linear layout, set its orientation to horizontal, set the padding, set the gravity, then we have to create another view, that view as the child of the linear layout, and so on and so on. So it's very tedious, it's a lot of code, it's easy to get wrong, and it's particularly difficult also to read and follow along, especially if you build a very complex UI that way. Good luck maintaining it if you have to go modify it a few months later.
So Android has the interesting approach where there is mostly imperative code that you write, but there's also this nice declarative aspect where you can set up the visual information of the layouts and how these things are structured around each other in XML instead. So we have imperative for actually performing the actions in the application, and then we have the declarative saying, and these are the UI elements. But there's this fragile barrier between them where one side needs to get information from the other. So the imperative needs to know what are these objects that I'm interacting with, which is why we have things like find view by ID.
And it doesn't quite help when you want to dynamically create the UI. So let's say you have a linear layout and you want to add an unknown number of children at runtime. You will end up doing this weird mix of declarative and imperative code that makes the whole thing a little more confusing than it should. Of course, there are other ways of doing this. The most recent one on Android is Jetpack Compose, which is both declarative and reactive. And so this is building the same UI, right? Except the tree of widgets is much more obvious on screen. It makes the code a lot easier to maintain, a lot more readable. And also because of the reactive aspect, you don't have to muck around with listeners and setters and updating the data. You let the system do it. And of course, this kind of systems are pretty popular nowadays, and you can find them on other platforms on the web and so on.
So now let's talk about how these things actually get structured in code in relationship to each other. Most UI toolkits, I think in history, in fact, all of the UI toolkits that I've worked on prior to Compose were based on inheritance. So you have some generic object at the top, and then Android, that is a view object that has sort of the base capabilities that all of these visual elements are going to have. And then below that, you have these subclasses that inherit behavior. So here in our simple example, we have an image view, then we have a view group, which is a container to hold other views. We have a text view, which is then a superclass of button. So all of this is fairly straightforward. It kind of makes sense until you look a little bit more closely, and then you have awkwardness where this means that button will inherit all of the capabilities of a generic text view. So now you can have autofill on a button, which is a little difficult, and it makes it harder and harder to maintain in the future, which is actually one of the reasons why we originally looked into doing something like Compose.
And it's very tempting to build and structure UI Toolkit that way, because with object-oriented programming, you know, you deal with classes and so on. And it's one of those situations where they're painfully obvious on screen, right? When you see a button, it's so natural to say, okay, I see a button on screen, it's a button in the code. It's not always the case with, you know, other aspects of object-oriented programming. So that's why, like, I think this was so popular. And even when you look at UI Toolkits built for, let's say, the C language that doesn't have classes, you're kind of doing object-oriented programming, but without classes.
So another potentially fragile aspect of this is when you want to customize, like we expected people from the beginning to customize these widgets. We didn't expect to provide everything in the platform that you would ever need. So you can create a custom view or a custom view group, which is great and it's very doable. On the other hand, you end up handling a lot of functionality that may not be obvious from the outside, and you end up writing a lot of boilerplate code. So if you want to write a custom layout container, well, you need to understand layout and measurement in addition to potentially the rendering aspects of that thing, because all of that functionality is being passed down through the tree, and you need to handle it appropriately in your subclass.
And more importantly, you have a very rigid structure, so you can only customize what can be extended. So if any of you have ever tried to customize a text view, you probably realize that you're very limited in what you can do. And very often when developers have asked me, like, hey, how can I do, you know, foo with text view, the answer was, go in the source code, copy the thousands of lines of code of the entire tech stack, and have at it. And it's a horrible answer, right? But there was no other way of doing that. The alternative is when you build the API as the author of the API, make as much as possible overridable. The problem with that is you paint yourself in a corner in terms of how the toolkit works, you know, what you can change in the future. So it's really not a great way of doing that. A better way, again, it's what we adopted in Compose, is to favor composition instead of inheritance. So the idea here is that you never extend from a base class. Instead, you compose together different behaviors. On top of that, Compose doesn't use classes. We use a functional approach where every widget is just a function that happens to emit state, and that state is going to be the tree of widgets that we build. So here you have the same example on screen. You know, you just create a function called custom in that case. That's all you need to create your new widget. And then if you call the layout function, you start doing your custom layout. There are many other ways you can build UI toolkits. I'm going to show you an interesting one. So this one is called IMGUI. It's actually written by a French developer. This is very popular in the game industry. So it's for C++, and it's called an immediate mode toolkit. Because it's targeted at games, in this toolkit, you rebuild the UI on every frame you paint. What's interesting about it is that it lets you write code like if button next, and then you open the braces. So what this does is that if the user clicks the button, then the content of the if statement is going to be executed, because the entire toolkit only lives effectively for the duration of the frame. So you can do this kind of stuff. So it's kind of nice because it's declarative. It's in a way reactive, because you're always reading your data frame over frame. But it can be difficult to build very complex UIs this way. But if you're interested, I highly recommend you take a look at this one. It's a very interesting toolkit to play with. So today we're going to show you the toolkit that we built. We call it Apex. Just I needed a random name. And let's see if I can do live coding. Sorry, I have to look at my monitor down there. All right. So there's a bit of setup that you can ignore for now. We have the set content function. Chet's going to talk about that in a little bit. And we're going to start building the UI we just presented. So we're going to start with a column. I'm going to center that column horizontally and vertically. So we call alignment. Then we call it a second time. All right. Then we're going to add some padding. Let's see, 16. And then we're going to add a row of buttons. So you can see it's quite similar to Jetpack Compose if you're used to it, in the sense that we're using functions, but it works quite differently. And then a second button. It's very hard to type with the screen not in front of you. All right, let's run that. Ta-da! We have beautiful UI. Thank you. All right. So it's not very interesting so far, so we're gonna look at how it works and what those things actually do. So let's go back to the slides. All right, so the architecture. So Apex uses what can be called an entity component framework. It's based or inspired by something called entity component systems that are, again, very popular in the game industry or in real-time rendering engines. I highly encourage you to go look at entity component systems if you're not familiar with them. They're very interesting. But effectively here you have the entire architecture of the toolkit on screen. So every widget is called an entity or an element actually in the Apex code, and it can have children. So an element can have children. So your column can have buttons and so on, and it can also have components. So components can be anything you want. It's arbitrary data or it's arbitrary behaviors, and we're going to see how we use those to build our UI. So if we go back to the example I just typed on screen and we map the code to the structure, so we have a row, so that's our first entity or our first element. Then when we add the alignment, the horizontal alignment, it's a component. It's just this value, this enum, is just added to the entity as a component. Then we do the same for the second alignment. Padding is also a component, so just a bit of data we attach to the view. Then when we create a button, it's another entity or element, and same thing for the second button. So again, you can see like a similar structure to the view system where you have this tree of pink boxes, which are going to be the widgets themselves, but then you have this secondary aspect, all those components, right, that are data and behavior. And with that, you can create widgets and not just the final UI. So if you look at the implementation of the row function that I was using to do this horizontal linear layout, it's an entity, it creates an entity that contains only one component. That component is a behavior, and it's a layout behavior, right? Its job is going to be to lay out its children. That's all it is. Now, if we look at the button, it's slightly more complicated. So that's what a button is made of. So if you look at the button function, it creates an entity or an element. It has a button model. So the button model is basically the public API, right? It's going to be the label of the button, your click listener, all the things that you want to set as the developer. It has some internal state. That's how it tracks its measurements, the press state when you click on it. It has internal padding. Then it has, and all that stuff is just data for now. And then it has layout and render, which are behaviors. So they're components that are in charge, obviously, of doing the layout and the rendering. And finally, there's motion input, another behavior that's going to be in charge of handling clicks.
So notice the difference between what we're seeing here and what we were talking about with inheritance before, where inheritance, all of this capability got passed down through all of the widgets in the system, which meant that button had the baggage of text view and view above it. Whereas here, everything is a generic element, and everything is provided with the capabilities through composition to do whatever it needs to do at runtime instead. So there is no inheritance baggage. There is no difference between any of these different elements. They all know how to handle themselves.
And you can reuse those elements. So if you take the motion input component here that recognizes a click, if you were to write, let's say, a checkbox, you could just reuse that component to handle the click, right? You can reuse bits of logic instead of having to override an entire class in really awkward ways. So if you go back at the code that I just showed you, here I'm using convenience functions. So those functions like row, alignment, padding, they just hide the calls to the actual APIs of the system. So if I translate that to the actual APIs, it looks like this. So the alignments are just components. So like I said, we're just adding enum values as a component to the elements. Same thing with the padding. And then the two buttons are add child. So we add them as children. So armed with that, we can build our own widget. So we're going to build an image widget so that you can see how one would build a widget inside the UI Toolkit. So to build an image, we need an image model. That's our API. So it's only going to hold a bitmap. So you can choose what to display. And then if you were to write the component with those low-level APIs I just mentioned, so add component and add child, it would look like this. You would create an instance of element. So that's our image. Then we would add a component. We'll start with our model. So we need to hold the data, so the bitmap. Then we're going to add another component. So we need behaviors to do the layout of the image. Then another component for rendering. And finally, we can add our image as a child of the column. So it's interesting, right? Because you could build your entire UI. For instance, I showed you the button function. It contains all those components. You don't need that button function. Like the framework doesn't, the UI Toolkit doesn't need to provide you that. You could write that code every time you need a button. You could do all those add component, add child, and so on. Obviously, that's cumbersome. So that's not what we want our API to be. Instead, we want our API to look like this. So let's write some code. And let's see. Where did my IDE go? Hey, it's back. All right. So we want to write our image. So we're going to start by creating our data model, just a data class. And then for convenience, image is going to be an extension function on element. So when we're inside the column, this block here runs on the element type. So that's how we could call the image function on an element to add an image as a child. Here we're using another convenience function called child element. If we look at the implementation, it instantiates the element and then adds it as a child of its parent. So it doesn't do anything very interesting. All right, so next we need to add our model as a component. Then we're going to do the layout. Oops. All right, so this layout function, similarly, is just a shorthand for add component, and it creates a layout component, it does the overriding, but it's easier to look at it this way. So here it doesn't do much, right? It looks at the aspect ratio of the image and figures out the final size that the image should have. The part that's interesting is that to figure out its size, it needs access to the bitmap. And the bitmap comes from the image model. So we have this API on our element called component, and we can query any of the components that are installed on the element. So in this case, I'm saying, hey, give me the image model, and then I can pick at the bitmap, and then I can look at its width and height and do the work I need to do. So that's a very important aspect of the system. Same thing in entity component system. You need to be able to look up those arbitrary components that you might have installed on your entities. And then we're going to do the rendering. Here we go.
You type really fast.
Thank you, Chet. All right. I need a paint. Yeah. All right. So render, same thing as layout. It's just a component we're adding to our element. And you can see here we're doing two things. We need to look up the image model to get the bitmap that we want to draw. And we look up the layout component so that we can get the bounds that we computed during the layout pass. And then we just do a call to draw bitmap. So now we can use that image in our beautiful UI. Image. I don't know why it typed all that code for me, but I'll take it. And if I rerun the app, here we go. We have an image.
Ta-da.
So, and you can see like the nice thing about this approach of components and elements that you could extract all of this and reuse it somewhere else, right? It could be a function you have or an object that you have that you could use in multiple places. It's also a lot less scary than what you have to do with the view system. But let's go back to the slides. So components, they are arbitrary data or behavior. You can look them up on any entity or element. And you can look up any entity or element by its components. So I have an example of that. So let's say that now in our demo, we want to be able to click the buttons to do something interesting, because right now they don't do anything. So we're going to add click handlers, but what we want to do is, like, as we go through the list of images, we need to change the enabled state of the buttons depending on where we are in the list. So to be able to do that, when I click the next button, I need to be able to reference the other button to change its state. So I need some kind of ID to be able to identify those widgets. So the really cool thing about the component system is the UI Toolkit itself doesn't have the concept of ID like you have with the view system, right, where you do find view by ID. But because I can add any data I want to an element, I can do it myself. So I can say add component, and here I have a small enum, so you can see it at the top here. It's an enum I created. Then I'll do the same for the other button. Button next. So now we're going to add the click handlers. So the click handler, Looks like a lot of code. But the part that's interesting is here I'm calling require child button next. So this is just a helper function that will go through all the children and find one that has a component of that type and that value. So that's how I can look up the other button, get its model, and then I can change the state of the model to be enabled or disabled. And we're going to do that for the other button as well. So it does the same thing. And when we run that, now we have an interactive UI. Yay! So, and that's pretty much it. That's what a UI toolkit is. So here I have this hand wave. So now that you've built an image, you just do that again for all the other widgets in the UI toolkit. And that's what takes a lot of work, because now you need to create the radio buttons, the checkboxes, all the layouts, and so on. But that's pretty much all you need, except, so now we build a structure, but we need to be able to integrate our UI tree with the system, so to draw it, and that's what Chet is going to describe next.
So everything that we saw so far is basically implemented directly on Android. It's using the underlying concepts to draw into Canvas to handle bitmaps and paints. This is all sort of handled as a part of writing Apex, but the general job that you need to accomplish with any UI toolkit is how do you hook up to the native platform. There is a way that the native platform is going to expect pixels to land on the screen. You need to interact with the rendering system somehow, and you also need to interact with the input system to actually figure out how to get input from the user. So essentially you have these two sort of functional blocks to implement to get from your UI layer at the top down to the hardware where the stuff actually gets displayed and interacted with the touch events from the user. So in Apex so far, we've seen things like this. So you have the ability to display an image, which is the bitmap object. You have the ability to change the rendering operations, the color of the button, the stroke width, the type of the text, the font, whatever it is. That is handled in Android's Paint object. And then you have the canvas, which is where the drawing operations happen, right? So you have the objects that you want to render, you have the style that they want to be rendered in, and then you have the actual operations where you're going to draw text, draw a button, draw a line, whatever. And underneath that, then you have the concept of a surface, which I'll get to in a minute. Beside that, then we have an input system. There's going to be some native way that the platform is going to handle input, and you need to plug into that somehow, which we handle in Apex in the OnMotion event. We're just handling normal Android input events there. So wouldn't it be interesting if you took this generic concept of a UI toolkit, which we have with Apex, and you abstracted it away and said, well, let's make it even more generic and not make it specific to Android. So what do we need to do to accomplish that? So we need to basically create abstraction layers on top of all these concepts. Every platform I have ever worked on has these concepts, right? They are represented differently. They have different kinds of attributes. They have different amounts of these attributes and capabilities, but essentially they all do the same kinds of things. They have a way of handling images. They have a way of handling painting style, drawing colors, drawing text size, stuff like that. And they have a way of actually getting the pixels to the screen. So we need to abstract these concepts away and provide generic APIs that will then bottom out into platform-specific APIs on whatever platform where you want to run the UI toolkit. On the other side, on inputs, again, there is always a way of handling input on the native system. We need to figure out what that is and then provide an abstraction layer on top of that, which then on an Android system would bottom out into the touch listener stuff that we were looking at earlier. So we have created a generic way of rendering, which is abstracted away from Android by creating this renderer API, which is going to be passed into all of the elements for them to render. So there's some concept of position. This would actually, in the long run, this would actually probably be a matrix or a transform because you want more than just a position. You want the ability to probably rotate and do something more interesting than just setting an XY point. But for now, position will do. And then you have the operations that can be handled. In our case, we're not doing much so far. We don't have that many elements. So we need to be the ability to draw some text, draw an image, draw a round rect, and that's pretty much it for now. But we still need this thing to actually render on Android. None of this is going to work on Android because these are not Android concepts. So underneath that, there is a subclass of renderer that does the implementation, or implementation, I think renderer is an interface is how it's implemented. details, doesn't matter. In Android, to create one of these objects, you pass in the canvas because that is the hook between this generic I want to draw something and the actual specific here is what it is going to draw to on Android. So you create the renderer passing in the canvas object, and then in each of these rendering functions that are called from the Apex code, it says, hey, I want to draw text, and it says, okay, I know how to do that because I have this canvas object I'm going to call canvas on Android. So let's talk about drawing surfaces. All of this stuff is good, but where do the pixels actually end up? All platforms have the concept of a drawing surface. They call it something different. But on Android, it is called a drawing surface, or it is called a surface, and you get that surface in various ways. So for example, you can use a surface view and request a surface from that. You can use a texture view. You can get it from the window. Generally, anybody writing UI code on Android, you may not have actually created or had direct access to a surface before because you get it automatically, implicitly. When you use Canvas, when you get a call to onDraw, you are drawing into a canvas, and the canvas has been supplied to you from the surface that was created on your behalf. So when your activity comes up, there is a surface that gets created under the hood, and every time the rendering operations are called, they pass a canvas which is created for that surface. All right, let's take a look at the activity code. We saw a little bit of this earlier. There's a set content that takes a lambda. This is an awful lot like your concepts that you use right now, which is the set content view. But this basically says, okay, here's the layout that I want to use. This is in the activity in the demo, the Apex demo that we were seeing earlier. So we've got this column. We have some of these components here. We have the image, and we have the row that has the buttons. This is going to be passed in to the set content function here. And it does this typical set content view where it gets the surface or gets the view from the surface view so that Android knows where to put these things correctly inside of the typical Android activity window that it has. And then it adds this callback that starts the rendering loop. So once the surface is created, we're going to call the root element so that we can actually start the engine running. We're going to do that. So our rendering loop is handled using choreographer frame callback. This is basically something where you can ping choreographer and say, I would like you to draw a frame for me, or I would like a pulse. And that is when you can actually draw into the surface so it can be displayed appropriately.
And what's interesting, if you went to the talk by Vadim and Pablo yesterday about Window Manager, so they explained a bit of how that works under the hood, like what are the windows and where do you get the surfaces from. They also mentioned something called ViewRoot impl. So ViewRoot impl on Android is this root element. There is this base piece of code that's responsible for connecting the underlying surface with the canvas of the view system. It's also responsible for triggering the first layout, the top-level layout, the top-level drawing, the top-level motion event dispatching. It's the exact same thing as what we call root element in our system.
And root element does here, I'm skipping a lot of code just to make it a little more concise for the slides, but root element also handles the layouts that's going on as well as the motion events. I'm not going to talk about input today. Leave that as an exercise for the reader. All right, now let's talk about the rendering loop. So any rendering system needs some sort of pulse, needs some sort of way to actually know when to draw stuff on the screen. In Android, that is handled via choreographer. This is basically the timing pulse, the life pulse of Android. On the vertical refresh rate, so every device has a different, potentially different refresh rate. Some of them have multiple refresh rates. And this is important to know for somebody like choreographer because you want to know what is the appropriate time for us to collect the rendering information and then display the rendering information. If we did it randomly, which we probably did earlier on Android, no, yes. It was always double buffered, but
it was random.
Then you have the potential of getting what we call tearing, where you're drawing at the same time as the screen is being refreshed, and you may be drawing the next frame at the same time as the previous frame is also displayed, and then animation stuff can look rather messy. Also, input events should really be gotten directly before you start drawing stuff, which reduces the latency between when the user taps on the screen and when the result of those taps appear as rendering objects on the screen. Working through the display sync avoids all those artifacts by basically giving the regular pulse that is synced with whatever the underlying hardware is doing to refresh the display. All right, so back to implementation. We're in this frame callback rendering loop, and basically every time around it says, I need a renderer object to pass into my Apex code, to pass into the app so that it can actually draw what it needs to. So it creates a new renderer object, and it creates an Android renderer, because this is the Android implementation, and it passes in the canvas that it got from the surface, which allows then the renderer to know how to draw stuff under the hood. And then the app code just gets this generic render object. It doesn't need to know what a canvas is. It doesn't need to know anything about Android. It just calls the renderer. I should point out here that we did a partial job of this. We didn't handle input events in an abstract way, and also you'll notice that there's a bitmap and a paint object here. These are Android concepts, so it's not completely generified. We only did the canvas portion of rendering. But again, we'll leave that as an exercise for the reader.
Speaking of exercises to the reader, so you should look at the source code. We just described rendering. You could also look at how layouts work or motion event dispatching works, because that would give you an idea of how the view system or Jetpack Compose work with a lot less code, because this does a lot less.
So there are many things that someone would do to turn this into a real toolkit that you used on multiple platforms here. The first is just do the rest of the widgets. So we did image and button, but there are probably a few more that you would need in the limit to actually have a full UI system. So you got checkboxes, progress bars, whatever those things are.
We also cheated a little bit, and we're effectively redrawing all the time, which means we don't have to worry about invalidation, right? Because we're rendering every frame. And a huge part of the difficulty of being a UI toolkit is to redraw and layout only when needed. So if you're ever interested in figuring that out, you can try it in this little experiment. But for instance, when I started on the Android team, that's one of the first tasks I was given was, hey, could you please optimize invalidation, because we're redrawing way too much.
I should point out that this is kind of a big difference between games and applications. Where games have a rendering loop, they are redrawing every frame. The assumption in any game that you play is there's always stuff going on the screen, whether there's an animation or some interactivity going on the screen, or the user interacting, running around, shooting more monsters, whatever it is. And so that's not really a problem there. They're not going for optimizing things for maximum battery life. They assume you want max performance and soaking all your battery life while you're in the middle of the game. On the UI, however, once that display is rendered and the user is thinking about which button to tap, you don't want to be refreshing the display, because that is an incredible waste of energy and power on the device, and heating up the device, and all of the problems associated with that. So there's an optimization that needs to happen for UIs that really isn't something that needs to happen for games. You also need to minimize allocation. So just like when Romain joined the team and started optimizing for not redrawing too often, there was also a lot of optimizations that needed to happen around not allocating objects when that didn't need to happen. If you think about UI Toolkit code or framework code compared to app code, the framework code really is the inner loop of the application. It's the innermost part of the inner loop. And so anything that a framework or a toolkit can do to minimize really low-level optimization or allocation stuff, things that are going to take up memory and time and GC and runtime and battery and all that stuff, needs to be tuned very carefully, or else you're going to use up the battery on behalf of the user.
Like Chet mentioned, we only did cross-platform abstractions for rendering, and not even all of rendering, like bitmap and paint. So that's another interesting thing that you can try if you want to abstract more of the code to get an idea of how that can be done. And finally, what we've been doing for the past 15 years on the Android team, which is optimizing. Like, you're pretty much never done with the UI Toolkit. A lot of the work goes into optimizing all the time. And again, if you look at the source code of either Compose or the view system, a lot of the code is there for optimization reasons, more than correctness.
And then simply repeat this whole thing for the rest of your career.
Yeah, and so the key takeaway, it's very easy to create your own UI toolkit, but it's very hard to make it production ready, and because we never stop.
It's never right. It's never done. And when it is, actually, it's just time to create a new one.
All right, so we're done with the presentation, but we have a few minutes for questions.
Hi.
Hi, thank you for the talk. About the component getter method, it relies on the type of the component. So does that mean we can't have two components of different types? And is it a problem?
You mean two components of the same type? Yeah, you can have two components of the same type. We didn't bother giving you APIs to look at them, but you could iterate by hand.
Question way up there. Or maybe you were just waving hello.
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 That's it. I was wondering what bottleneck you encountered when you build Compose or any rendering system with the platform, and if you could change things in any underlying platform, what would you do to make Compose better?
What could we do to make Compose better in the platform? Oh, many, many, many things. You should look at your bug list, Vadim. No, like so for the case of Compose in particular, because the UI Toolkit was always built as part of the platform, there were a lot of things that were provided by the platform as private APIs, which then become not available to Compose, which limits what can be done. There are other things, like for instance, Compose uses Canvas, but Canvas is part of the platform. So if we need new features in Canvas, for instance, the blur effect that was added in Android 12, many people on the Compose bug analyzer are very vocal about wanting that blur effect in Compose on all API levels, and I very much agree with them. The problem is it's part of the platform, and it's not in the other platforms. So we would have to write fallback, which can be very inefficient. So yeah, it would be like more layering, more extracting of the platform into unbundled libraries that we can update, stuff like that. There's a question here.
Just about the compiler. You guys built the Compose compiler. Was that a big part of the work, or was it just a nice to have?
The Compose compiler, was it a big part of the work or nice to have? It was a big part of the work. So this example is interesting because there are things that Apex need to pass as parameters that are therefore exposed. But in Compose, we can hide all that machinery because the compiler generates that code for you. So the compiler was really helpful. What the compiler does also in Compose is help doing all the tracking of state changes. There's also runtime associated with that. Without that, you would end up doing a lot more by hand, maybe having like manual invalidation calls, which is nice because we don't have them in Compose. So yeah, it was very important to make Compose what it is today.
So for example, one of the reasons that we wouldn't need the state invalidation machinery of the compiler is because Apex just renders at every single frame. Right? There's a rendering loop and it wakes up and it draws everything. Horrible waste that needs to be optimized. The approach that Compose took with a Kotlin compiler was one of the approaches to doing that. Time for one or two more.
There's another question here.
Here we go. In the middle? Go, shout it out. Go ahead.
Over the 15 years where you worked on view systems, what was the most impactful optimization that you managed to do?
So over the 15 years that the view system was being worked on, what was the most impactful optimization? Couple.
There were, I can think of one, which was moving all of the view system to the GPU.
Yep.
If you can call that an optimization.
Actually, related to that was a minor optimization on top of GPU was moving to displayless. Not minor, but the ability to then package up and sort of figure out what had changed at a really small level for each node going down, as well as properties, which encapsulated some of the very common things like this view just got moved by being translated during an animation, and this can be done at a very small level without sort of invalidating everything else around it. Some of the earlier stuff that Romain mentioned was hugely important as well, like not drawing on every frame, as well as not redrawing the entire screen every frame, which is basically the way the toolkit worked in 2007 when you joined. Anyone else? C'est fini?
All right. Thank you very much.